Hello everyone, welcome to gRPC Conf. My name is Gina, and I'm a gRPC maintainer. In this talk, I will cover gRPC's core concepts and its life cycle. If you are new to gRPC, you will learn a basic concept of gRPC. And we also have hands-on code labs available all the day in the breakout rooms for practical experiences. For those familiar with gRPC, this offers a quick refresher to prepare you for a full day of rich topics and advanced use cases. So let's get started. gRPC is an open source, high-performance remote procedure call framework. It's easy to use, incredibly efficient, and has become the go-to standard in the industry. In simple terms, think of gRPC as a high-speed delivery service for your data. It reliably and quickly transmits the information between your services and applications over the internet. gRPC's popularity stems from its versatility and high performance. In addition to being available in a wide range of programming languages and platforms, its performance is industry-leading. The framework features a pluggable architecture, allowing for flexible and efficient integration with various development stacks. Furthermore, gRPC offers a rich feature set for traffic management, security, and service mesh integration. A key design choice of gRPC is using protobuf as its IDL to structure the service messages. Protobuf's use of a binary encoding format results in smaller message sizes and highly efficient parsing. This benefits directly to gRPC's high performance and high flexibility compared to other RPC frameworks. Another fundamental design decision of gRPC is that it's built on top of HTTP2, ensuring the compatibility with many existing load balancers in its process. HTTP2's use of header compression, binary encoding, and multiplexing over a single TCP connection makes gRPC a high-performance framework that reduces the network latency and uses resources more efficiently. Now let's take a look at gRPC's core concepts, and it starts from a channel. A gRPC channel is an object that represents a virtual connection to a gRPC service, identified by a target URI. A gRPC channel is responsible for managing TCP connections to the servers, and you could have 0, 1, or many connections, depends on the needs of your applications. The channel is also responsible for handling key functionalities like name resolution, load balancing, so you don't have to do it by yourself. And I will cover that in a few minutes. After establishing the gRPC channel, you create a client stop from it. This stop, generated from your protobuf definition, is the object that you use to make remote calls. When you invoke a method on the stop, it initiates a logical call within the gRPC runtime. The call is then mapped to a HTTP2 stream at the transport layer, which handles the actual data transmission. Essentially, an RPC, a call, and a stream, all referring to the same fundamental idea, is just different terms that was being used at a different abstraction layer. Before a gRPC channel can connect to a server, it must first perform name resolution. This is because applications use the target URI to specify the service to connect to when creating a gRPC channel. But the underlying transport requires the specific IP address to establish a connection. In gRPC, name resolution is the process of figuring out the IP address of a server from a given URI. Think of it as the gRPC equivalent of phone book. When the client wants to call a server, it uses the server's URI to look up its addresses before establishing a connection. While this sounds a lot like what DNS does, gRPC's name resolution is more flexible. It has a pluggable architecture that allows for different strategies to find the server addresses. Name resolver then returns the service config to the next component, load balancer. The load balancer manages open connections towards the backend servers, and then distributes the request among multiple backend servers based on the service config. gRPC offers the built-in load balancing with several common load balancing policies, such as round-robin, weighted round-robin, list request, and the default is peak first. Load balancing is one of the most critical components within gRPC. If you are interested in learning more about how it works and best practices, we have a Birds of Feather at 3:30 today, and we also have another talk from Iswa at 4:10 to deep dive into the load balancing details. So once the connection is established, gRPC serializes the request data and sends it in frames according to the HTTP2 protocol. The server side mirrors the client side. The server transport receives the request and then notifies the application. The application server logic will then process the request and then returns the response to be sent back to the client. gRPC supports 4 types of communication patterns, and you can choose the one that best fits of your application's needs. Unary is the classic request-response model. The client sends a single request and gets back a single response. Server streaming, the client sends a single request and gets multiple responses. Client streaming, the client sends multiple requests and gets back a single response. Last but not least, bi-directional streaming. Both the client and the server send independent streams of messages to each other. Now that we've covered the gRPC lifecycle, let's move on to a few other important features. And the first one is interceptors. gRPC interceptors is a powerful middleware component that in the gRPC framework that allows you to intercept and modify the request before or after they reach the intended destination. As shown from the graph, there are certain points that gRPC will call to run your interceptor tasks. Interceptors provide a clean way to add cross-cutting concerns such as authorization, error handling, and more to your gRPC services without cluttering your main application logic. Deadlines is another feature provided by gRPC, and it is a client-side mechanism to prevent RPCs from being running indefinitely. The client specifies how long it's willing to wait for a response, and this timeout can be set either as a fixed point in time or a duration. If the time is exceeded, the call is canceled with a deadline exceeded status, and it can happen for various reasons, such as a failure connect to the server or a server recognizing that the client deadline set by is simply too short to fulfill. Crucially, gRPC supports deadline propagation. When the server receives a request, it also receives the associated deadline. If that server then makes its own RPC to other upstream services, it automatically forwards the remaining time, ensuring that the original client time limit is enforced across the entire distributed systems. This is a crucial safeguard against the network latency or server issues, and we highly recommend you to always set a deadline or timeout in your application. In addition to deadlines, gRPC clients can manually cancel an RPC it no longer needs. The cancellation signal propagates through the HTTP transport to the server, allowing it to stop processing and clean up the resource. For this to be effective, especially for long-lived RPCs, a server handler should periodically check if the call it's servicing has been canceled. Upon detecting a cancellation, the server should stop processing immediately and clean up the resources, and ideally propagate the cancellation to any downstream services it may have called. gRPC Retry is a feature that allows clients to automatically reattempt an RPC call if it fails. It's a powerful mechanism for building resilient applications that can gracefully handle transient server-side issues or temporary network problems without requiring adding complex logics into your application code. When you enable gRPC retry, the client channel is configured with a retry policy. This policy defines the rules of reattempting of a failed call, such as max attempt, backup delay, and retriable status code. When criteria are met, gRPC will create a new retry stream after the exponential backup delay. Once a response is received, no further retries will be attempted, and gRPC will hand over the call to the application. If you have observability enabled, you will see the retry metrics, including details like retry attempts and backup delays for each of the call. We have a gRPC observability talk from Yash at 4:40 today, and join the talk if you are interested to learn more about gRPC observability. Every RPC will eventually terminate, either successfully or with an error code. This termination of the call is communicated through the status code, which informs the client about the outcome of the RPC. It's important to terminate the gRPC channel properly when you are shutting down your application. You can initiate a graceful termination using the shutdown method, which rejects new calls, but allows for any in-flight request to finish. Since the shutdown is asynchronous, you must wait for the process to complete. You can use the method await termination to block until the channel has fully terminated or a certain timeout is reached to ensure a clean exit. For a more immediate stop, the shutdown now method will forcefully cancel all the ongoing and new calls. To summarize, we began from the fundamentals. gRPC is a modern, open-source, high-performance remote procedure call framework. It's built on top of protobuf and HTTP2. We also walk through the lifecycle of a gRPC call from channel creation, name resolution, to load balancing. Finally, we cover several advanced use cases and best practices that are key to build a robust applications. Using interceptors as the powerful middleware to modify the gRPC call before or after they reach the intended destination. Setting deadlines or timeouts to prevent RPCs from running indefinitely, and deadlines will be propagated to upstreams if any. Using cancel if you're no longer interested in the results of the RPCs, and the server handler should periodically check if their call has been canceled before processing the request. Also, propagating the cancellation to any downstream services is highly recommended. Configuring retries for fault tolerant and resilience, and gracefully terminating the gRPC channels during the application shutdown. This brings us to the end of my talk. Thank you for your time and attention, and good luck with your gRPC application. Thank you.